Um, Let me know what's going on. I think the quiz was due there. Yeah, the quiz was due. We'll have another quiz next week, and that'll be kind of yes, patio furniture. We're doing that there on the weekend, but we're looking at what the assignment is out. Um, and Yeah, so this is where we're at right now. I hope you guys are doing all right. We have our final test in 2 weeks, and it will be. I'm going to try to have it around the our our class time is Thursday 1 to 4. That's our scheduled time. So I'm going to try and have it in and around there. But I still want to be a little accommodating because I know people have kids and jobs and now we're looking at another shutdown again. That started there last night. So I hope you guys are doing all right. Are there any emergencies at the moment? Anything there that needs to get fixed like right now? Um, if there is, let me know. If you see anything there that I'm not seeing, yeah, let me know. Yeah, the Esther Lab is all right. It's actually thanks Jennifer for that. The Esther Lab is actually a lot more fun in person. All these labs are honestly, everything is more fun when you do it in person, right? So, but you guys are just 2 weeks away from finishing pre-health, and I want you guys to don't revel in your own magnificence yet. Okay, you guys have worked so hard. Your averages are great. Your hopefully your acceptances aren't conditional, and you guys are kind of coasting. But if they are, just keep on trucking, man. You got 2 weeks. Get everything done. You don't hand in one silly lab. Now, the best mark you can get if you got perfect on everything else is 95. So you hand in everything. All right. And if there's any issues, and there have been issues, you come and you talk to me. I'm the issue fixer. All right. So if something isn't, some questions bothering you, I don't know if you're having issues at home, please, I don't need to know details. I just need to know, I just need something emailed to me and then we can work something out. Okay. So just please be safe out there. Stay focused for another 2 weeks and then it's all over. All right. And then you guys are moving on to greener pastures. But I haven't heard anything, so I guess everything is okay right now. We'll start up the lecture right now. Honestly, we're into if the week 8 lecture. Sorry, I'm trying to find my camera. The week 8 lecture, the week 9, the week 10. You know what I mean? These I want you guys to kind of see that there's a complete repetition happening here. And you'll see this in here because today we're doing carboxylic acids and esters. We're going to do a little bit of amines as well. You're going to start to see we're walking over the same carpet again and again and again. And it's all based on basically the week 8 PowerPoint. You know, that important slide there that I showed you, meth, eth, prop, and nothing's really changed from now. Carboxylic acids, we're just, if you have a pentane and a carboxylic acid, it'll be pentanoic acid. These kinds of things. And again, this is all we're doing there today, and I don't plan on keeping you here for more than an hour anyway, because it's too nice. So, Ian, shut up, and let's get moving, shall we? I hope you guys are well, and if there are any issues, just stick around after. I think I've got one student there I'm going to talk to. All is good. If there's any issues there, just let me know, okay? Because we still have time to fix things. We have 2 weeks. If you are anticipating an issue late next week or, you know, this kind of, let me know, okay? Just shoot me a quick email, whether bad tidings are ahead or you don't really know, but, you know, keep me in the loop in some respect, okay? And we can get things going. Okie dokie. Here we are. Aldehydes, ketones, carboxylic acids, and esters. Okay. So this is, yeah, week 11. I have two schedules here. I have a Lakehead and a Georgian. Momentarily confused. Aldehydes, ketones, carboxylic acids, and esters. Okay. You guys will remember this. This has been kind of a common theme. We started off with alkanes. This is the oxidation reaction of an alkane. And we can oxidize an alkane, okay, and that will throw an alcohol group on there. We can further oxidize the alcohol group. Now you remember, if it's a primary, now I'm going to start recalling stuff there from week 8 and week 9 in anticipation there that this is not only knowledge that you've just recently acquired, this is knowledge there that you can now utilize. Okay, that's where we're at right now. So a primary alcohol, you'll remember, is an alcohol group attached to a carbon that's only attached to one other carbon. A secondary alcohol is an alcohol group attached to a carbon that's attached to two other carbons. A tertiary is the alcohol group attached to a carbon that's attached to 3 other carbons, okay? The chemistry, the reactions will be different. So if this alcohol is a primary, okay, we can make an aldehyde. And then that can be further oxidized into a carboxylic acid. If this is a secondary alcohol, this will oxidize into a ketone. And then it will, and that's as far as it goes there for a secondary. If this is a tertiary, none of this happens. It doesn't oxidize any further, okay? Just a bit of review there. You will see that because you can see there, we did this there week 1, we did this there week 2. We did, was it aldehydes there last week? And here we're on to carboxylic. So this will be on the final. You'll remember there the carbon. I'm in a good mood. And who wouldn't be in a good mood there with the window open and the sun out? You guys will remember there your carbonyl group, the C double bond O. Okay? Carboxylic acids have a carbonyl group. Ketones have a carbonyl group. Aldehydes have a carbonyl group. Yeah, something like that. Okay, and the oxygen, again, just augments the chemistry very much so. Okay, and because of these 2 lone pairs of electrons there on the outside of the oxygen there, this is very electronegative. Loves to scoop up electrons and make this area here negative. Carbonyl groups and aldehydes, ketones, and carboxylic acids. This is a little bit of review here. Your aldehydes and ketones, they are very much related. Okay, but aldehydes exist on the end. Ketones exist in the middle. All right. And here's examples here. Okay. There's your ketone in the middle. Your aldehyde is on the end. Okay. And no, I'm not blocking anything here. Carboxylic acids, you'll see them written a number of different ways here. I've never seen it written like this. Ugh, ugly. I will write it like this, or you'll see it written like this. Okay. Aldehydes and ketones, the aldehyde group is often written as CHO. Okay. And there's your aldehyde group, and here is your ketone group in the middle. Okay, so they're basically the same. Aldehydes are on the end, ketones are in the middle. This one here, I've shown you guys pictures of this in various different forms when we're talking about different, what's the word I'm looking for? Functional groups. And here we're talking about solubility in agua. All right. And water is a polar molecule, lots of hydrogens in there, and polar likes polar, right? Well, generally, how we're dealing with these guys here, smaller carbon chains will generally go into water. And I don't want to say a blanket effect, but the smaller the carbon chain, the more readily it will go into water. Because the carbon chain, right, carbon, 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 carbon with all the hydrogens there, right, it's an aliphatic chain. It's completely non-polar, okay? Like octane, heptane, hexane, pentane. They're absolutely 100% non-polar, okay? And you got to think, vegetable oil, okay? It's a carbon-based oil, does not go into water because of the carbon chains there. They prevent this thing from going into water. And you'll see here that for aldehydes and ketones, all right, they have this oxygen in here, which is, you can't get any more polar than that. And you see here you have, like, let's look at, what is this, ethanol. All right, 2 carbons, ethanol. You have a very small 2-carbon chain. So the 2 carbons there are non-polar per se, but the oxygen trumps it. So this is an absolutely polar molecule. All right, and if you have a look at the slide, at this slide here, here's methanol, ethanol. Here we're just adding a carb, 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 carb. And you'll notice there that your small carbon chains, they go into water readily. Easy peasy. Methanol, ethanol, propanol, even propanone. Ketones aren't as soluble because the carbonyl group is in the middle. It's surrounded by the non-carbon or the non-polar chains. All right. Oh, seriously, I gotta close the window a bit. I start sweating. All right. So the longer the carbon chain, generally the less soluble it gets. Maybe I'll say it a different way. The smaller the carbon chain, the more soluble a molecule will become. And generally it kind of works across all groups. If you're dealing with, if you're comparing meth, eth, prop, and bute for aldehydes or carboxylic acids or whatever functional group, generally the more carbons you add to it, the more non-polar this becomes. And generally it happens around 4 or 5 carbons where something changes. And you'll see here that at butanone soluble and everything under it, 4-carbon butanol, 3-carbon propanone, 3-carbon propanol, 2-carbon ethanol, and 1-carbon methanol, they all go into water easy peasy. All right, because the oxygen, the 1-carbonyl group there, turns the entire molecule into a polar molecule. Polar likes polar, easy to go into water. But in and around 5 carbons or so, the 5-carbon nonpolar chain is too strong of a nonpolar idea there for the oxygen. So at about 5 carbons, the nonpolar trumps the oxygen. Isn't that crazy? Eh? You need 5 carbons and all of its hydrogens to trump 1 oxygen atom. Crazy. Yeah, so have a look at this. Have a look at previous slides because there are going to be a couple questions. I think they're on the assignment or the quiz there. There was, I think I gave you 4 or 5 molecules and I asked you to rank them in order of solubility. I think that's what it was. And so these are good ones there to have close at hand. But just know that the magic number is around 4 and 5 where things start to change as far as solubility. Yeah, and that's just, it's saying the same thing. Okay, it's the carbonyl group is everything. Okay, the electronegative O atom on the carbonyl group of aldehydes and ketones forms hydrogen bonds. And without hydrogen bonds, this thing ain't going into water. Okay, any issues on that, let me know. indicate whether each is soluble or insoluble. So you have a look at this one right here. Here I got 3 carbs and I got 8 hydrogens there. 100% nonpolar. Okay, there's no oxygens, there's nothing pulling this molecule electronegative to the right or left or up or down. It's 100% nonpolar. It'll never go into water. Here I've got, and you should be able to name all these. You should be able to, easy peasy. This one here, 2 carbon chain with an alcohol. Okay, that's ethanol. And 2 carbon, it's under 5 carbons, so that'll definitely go into water. But if you check there, this is ethanol, 2 carbs. Check the solubility of pentanol, 5 carbons. Okay, it should go into water, but it probably won't like it too much, if it does at all. Okay, here I've got 1, 2, 3, 4. Here I've got butanol. Okay. And because of this guy right here, or sorry, I can't do it, the CO carbonyl group, that's why that one goes into water. And what do I have here? Propanone. It will also go into water. It's under 5 carbons. Okay. What do we got here? Naming aldehydes. Not too bad. Okay. We've got, you follow the same thing. Find your longest carbon chain, meth, eth, prop, but, pent, hex, hept. You get it? And if once you recognize there that that is an aldehyde, it's on the end, throw an al on it. Okay, methanol, ethanol, propanol, butanol. You will, if you see these names here, I wouldn't ask you, but formaldehyde, we've all heard of it. Okay, that's what they put into dead bodies to make them look, preserve them through the funeral process and these kinds of things. All right. Naming aldehydes. Okay. There are going to be some wonky ones out there, but you guys have your notes. This one right here, anything with benzene, double check. Okay. Like, who's the big boss here? Here we've got benzaldehyde, so that means that the aldehyde actually trumps the benzene. Okay, so this one here, benzaldehyde. But you guys have your benzene naming sheet. You guys will be fine on that. Name the longest carbon chain and away you go. All right. And like this one right here, I left this one blank, and this is missing something here. All right. Find your longest carbon chain, which is pent. And you'll see here that we've got benzaldehyde, but then we've got these 2 chloros on here, so we're probably looking at a dichloro somewhere. All right. And here are your answers there. When you're throwing numbers in, remember, if you're going to put a number in there, like right here, 2-methylpentanal, well, because I'm putting a 2 in here, there better be a 3. There can even be a 4. There won't be a 5. Okay. If that methyl group was on the end, it would now be hexanal. Okay. You start numbering from this carbon, 1, 2, 3, 4, 5. And you'll see here that with your benzene, there's your benzaldehyde. This will be your carbon number 1. Okay. I don't like that. 1, 2, 3. Aha! Look at that, eh? That should be 3, 4 dichlorobenzenaldehyde. Okay? So that's what we're looking for there. 1, 2, 3. And this one here is on 4. So it would be 3, 4 dichlorobenzenaldehyde. I'll update that on the PowerPoint there that you guys have. Okay? What do we got now? Aldehydes and flavorings. Okay. We've seen these there before. Almonds, benzaldehydes. You got vanilla. Okay. Cinnamon is also an aldehyde. All right. And you can see I'm throwing these in here because one of these little rinky-dinky little questions there, I could say, is vanilla an aldehyde, or is it a carboxylic acid, or I don't know. Some little silly one-mark question on a test or a quiz. Ketones, same thing. There was an issue with, I think it was this one right here, actually. And I just said it. If you're going to put a number on there, then there has to be another number that could also go on there, right? Like a 2 or a 3, whatever, just like we did there with the methyl group. There was an issue there with one of the questions, I think, on the last assignment, where you look at this right here. This is 1, 2, 3, 4, so it's a butane, right? No dubs or trips. And I've got this carbonyl group on the number 2. And I've always known this as butanone. There's no number on it, all right? Because if this ketone group, if this carbonyl group was on the side, it would now be butanal, right? Okay, so this carbonyl group is on the 1, 2 carbon. But if I put this carbonyl group on here, it doesn't become 3 propanone. Just flip it around 180 degrees, and it's still 2 butanone. So in this case here, there is no number needed. It's just butanone. But I think, somebody found it in the book. And you can't argue with the book, can you? Because the book is just everything. And good on that person for finding it. Because the book was calling it 2-butanone. And it's okay. So I just deleted the question. That's all right. But my test there, I'm in the process of making it now. And I apologize for that mistake. It shouldn't happen again. But just as long as you guys know that that is butanone. And even though the book says 2-butanone, there is no other option for another number in there. So, this one here, propanone, count your longest carbon chain. That's how she goes. If I'm going too fast, just say, hey Ian, slow down. But you can start to see now that things are kind of leveling out. And the things there that we've learned together there the first couple weeks of the second half of this course kind of carrying through very strongly right to the end. So if there's any issues, just let me know here. Naming ketones, okay. Again, you start there to the shortest side of where the ketone is. Find your longest carbon chain. And again, you're working backwards, right? So find your longest carbon chain. I got 1, 2, 3, 4, 5, 6. So it looks like a hexane. Okay, and I've got this carbonyl group here. This is a ketone, so it'll be a hexanone. It's on the 2 carbon, so it'll be 2-hexanone. Please, when you're doing these, start from the back. All right, so there's your 2-hexanone. And 1, 2, 3, 4. 4-methyl 2-hexanone. So I hope these haven't stressed you guys out too much. Hopefully you guys have found the knack of these and they're more fun than anything. Please be careful with these ones here. People will try and name these as aromatic, like benzene derivatives or something. They're not. You remember, if there's nothing in the middle, well, this is a 5-carbon ring. Okay, and there's nothing in the middle there, so this is not benzene by any means, okay? So this is cyclopentane, all right? And then I've got a methyl group, and you see I write that. Cyclopentane, right there. That's and I know I'm writing it at the back, so cyclopentane. And then I got a methyl group, and a ketone. Which is going to trump what? The ketone's going to trump, so this is a cyclopentanone. Okay? And then this will be your 1 carbon, 2, 3, 2,3 dimethyl cyclopentanone. And you'll notice there that I don't need a 1 cyclopentanone because it's inferred there that the ketone will be at the carbon 1. All right. So if there's any issues with that, keep me posted. I'm not really, I threw this in here because you guys in your medical professions will see, like in the lab there, they come in from the factory with these old school names. So am I going to get you on it? There might be one question, I don't even know. Okay, but my focus isn't old school names. My focus is IUPAC names. Okay. So what do we got here? This is right here, 2-butanone. There ain't no, there isn't a thing called 2-butanone. But the PowerPoints here, which I've augmented a lot over the years, this is from the original company there, same as your textbook. So, hello.
Hi.
Hi. Do you have a question?
I put in the chat, but I don't know. Maybe you can't see the chat. But,
all right. Talk to me.
What does the cyclo indicate? Like, I know there's like pent or propyl, like those indicate how many carbon atoms.
Yeah.
But what is cyclo? Like, I tried to like Google it and I couldn't really
Hey, awesome question. Whenever you see a cyclo, like that is okay. Let's take a hexane. Okay, so it has 6 carbons. It'll be C6H14. That's a hexane is an alkane. It's a chain. But we can take that chain and put it into a circle. So now we have hexane. All right. The chemical formula is a little different. It'll be C6H12 because you've lost your ends where you'd have 3 hydrogens. Now your ends are tied. So you lose a hydrogen and lose a hydrogen. So that's why your chemical formula would be a little different. But whenever you see cyclo, that means it's an alkane or an aliphat. It could be an alkene. It could even, I don't think it could be an alkyne. But what it just means is it's a chain of carbon, like hexane or pentane or whatever, that's now in a circle. So you'll see here that I got 1 carbon, 2, 3, 4, 5 carbons. So if this was a chain, it would be pentane. Okay. If it was a chain with a ketone, it would be pentanone. But this is a circle. They're connected in some type of a ring fashion. So now we call this cyclopentanone. You can have methane. There's no cyclo for methane. There's no cyclo for ethane. Propane, 3 carbons, is the smallest one that can be a cyclo because you're going to get a triangle. Carbon, 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 cyclopropane. And you can get cyclobutane, cyclopentane, all the way up now. Talk to me. How'd that go, Shaylin?
Yeah, that's a bit clearer. But also when there's like, you know how there's the benzene ring or whatever, like, have the circle in the middle? I was just like flipping through my notes in the textbook and stuff, and I noticed that some of them still have the ring, but aren't like a benzene.
Yes. And
that they're double bonded.
Good. That's exactly it. If you see, I don't think I have one in this PowerPoint, but benzene, it's his own thing. It's not related to alkanes or alkenes or alkynes or cyclos or any. Benzene is a different ball of wax. All right. But where students get confused is they will see like this one right here. This is a benzene ring. 100% benzene because it's got a double bond here, double bond here, double bond here. And you will remember those bonds rotate. Benzene will also be written like this. Okay, 6 sides, and see this circle in here is indicative of the double bonds rotating back and forth. Okay, this and this are your only 2 examples that I will give you of what a benzene will look like. If you see a hexagon like this without a circle in the middle, it ain't benzene. It is cyclohexane. Guaranteed, I will put a question on there that tests that knowledge. Okay? And now you know, don't make the mistake. It's a free 1 mark on the test. All right? So if you see a 6-sided ring that looks like this or this, that means it's benzene. Ding, ding, ding. It's got its own naming system. It's its own banana. But if you see a 6-carbon ring without anything in the middle of it, I don't even think I have one here. Rats. Good question. Like this one right here. Okay, if this was 6 carbons, okay, it would kind of look like benzene, but it doesn't have any representation showing the double bonds in the middle. That means it is cyclohexane. Talk to me, Shaylin. What's going on?
Yeah, that makes a bit more sense. And this might seem like obvious or whatever, but I just want to make sure I'm doing it right, just because for the assignment or whatever. When there's the shapes, every joint or whatever is a carbon, right? Or is it a CH group? Because I was thinking that like the lines were hydrogens.
Excellent. Good, good, good. Just trying to think of what was benzene week 9. Well, I'll see if I can flub it here, and I'll see if I can. What do these straight lines mean exactly? Now, remember, how many bonds does carbon have? Carbon has got to have 4 bonds. So each one of these little corners right here is a carbon. That's all it represents. Now, let's just have a look at this one right here. Here, I'll blow up here. Great question. So this right here is a carbon atom. Okay, and this carbon atom is bonded to this carbon. So there's 1 bond. This carbon atom is bonded to this carbon. That is 2 bonds. What's going on here? Well, I need 2 more. It's implied that there's a hydrogen here and a hydrogen here. So there's 2 hydrogens here. It's implied. All right. So this is carbon with 2 hydrogens here. This is a carbon with 2 hydrogens here. This is a carbon with no hydrogens. This carbon is bonded to this carbon and to this carbon, but it's got a double bond going to the O. So just remember that carbon has got 4 bonds. And just because all 4 bonds are not represented in these line diagrams, you gotta account for them. Okay? And
so the CH3, it has to have at least 4. Is that what it is?
All right, good. So let's look at this carbon here. So this carbon is bonded to this carbon. There's 1. This carbon is bonded to this carbon. There's 2. This carbon is bonded to this carbon. There's 3. But wait a second. There's another hydrogen in here. Okay, so just these stick diagrams, they're nasty. Okay, but once you how you get around them, carbon has 4 bonds. What is not being represented here by this crappy diagram? That's the key. Talk to me.
Yeah, that kind of clarifies it, but when there's you see how there's CH3? So it's indicated that each joint or whatever is a CH2. So a CH3, would that technically have then 6 bonds?
No,
because there's 2 hydrogens attached to the carbon, the CH3, and then the CH3 is attached to another carbon that's attached to 2 others.
Yeah, you see, this carbon here has 3 hydrogens off of it. That's all that's going on here. Whenever you see a CH3, it generally means a terminal carbon, a carbon on the end of a chain. So this carbon has 3 hydrogens coming off of it, and it's bonded 1 time to this carbon here. So this carbon has 4 bonds.
Oh, okay.
All right. Where were you seeing 6? What were you...
I was just, because you were saying how in the other corner.
Yeah.
Yeah, right there. It's implied that it's CH2. So there's the 2 hydrogens off the carbon, and then those 2 lines are each a carbon bond.
Yeah.
So I was thinking that off of that carbon, the CH3, there's the 3 hydrogens, and then it's bonded to those 2 that it's branching off of.
Well, yeah, these ones here are written for ease of use. These ones here are written for laziness. Sorry.
Yeah,
All right. If you have any issues, stick around later. We'll get you squared up.
Okay.
All right. Hello. Any other questions?
Hi, I have a question about
Who am I speaking to? Alexander? Okay.
Yeah, it's Alex.
Yeah. What slide am I on here?
Gave us a sheet. Oh, it's not really about the slides. It's just kind of in general.
Yeah.
On the sheet that you gave us, was there sort of like a breakdown of like the hierarchy of like naming like within Orgo, or is it just kind of like a brief? Because I think a few of us are confused about like I understand that like some things will come before another thing, like in terms of like the ketone coming before like an ane or an ene or whatever. But is there like a breakdown sort of like the rules of the hierarchy? Because it gets kind of complicated with all of the different rules.
Oh, you haven't even seen anything yet. We're not even taking it. Like, this can get enormous and elaborate, and but we're just kind of keeping it here. That's probably a number. That's a top tier question. Is what outranks what, and we're just kind of giving you guys a rough estimate. I'm not going to give you guys a cyclo, an ene double bond with an alcohol and a carboxylic acid with a benzene. You know what I mean? There's 5 different things going on there. And no, we're going to keep it to where we're going to kind of keep it to the level of where the questions in the review questions there, the questions there that I give you, this is kind of where we're looking at. At best, I'll give you 2 or so things to deal with, just so okay, a ketone will trump a benzene ring. An alcohol group here will trump a double bond, these kinds of things. But as far as a list, we're not going to take it that far. We're going to kind of keep it as I don't want to say as simplified as possible. And if there's any specific questions there that you have that I can help you out with, let me know. But it's just a matter of, you've got your PowerPoint slides there, you've got your questions. The quiz there next week, that will be basically a precursor to the test. So the quiz there next week will give you a greater idea of what I'm looking for. The assignment you guys are doing right now, bang. That's your test in a nutshell right there. So if there's any specific questions there you have about this hierarchy issue, let me know, and we can work on that. All right, and if anything,
last semester that you did the formula sheet with the triangles last semester.
Yeah.
Do you think there's any way that you could do even just a quick sheet of just saying if you have this will come before it, of just the things we've reviewed, just so that I can keep on top of it, because I'm finding every week we're adding more, and then I can't remember which one goes over what, and I think a few of us are feeling like that. Is it okay to ask if we could have a little sheet of just the things that we've gone over?
Because there is nothing solidified. If I give you guys a sheet, then this is now etched in stone, and it's not. And as I said, I'm not going to give you 5 different competing things in one molecule. I'll give you 2, and you got to figure out which one is which one there is the hierarchy. And there's lots of examples there. Again, if you give me a specific question, then I can work from that, but I can't. So if you find one there and then throw it at me at the end of class here, we can go through it there with everybody, and we can talk about that for sure. Okay?
Thank you.
Oh, no, it's all good. And make sure you find one, because it's a good question, and it's not easy. It really isn't, and it's a valid question. Give me find me a question there at the after, or find me 2 questions, and we can talk about them there for sure. How's that sound, Alex? Okay. Good.
Yeah, thank you.
It's all good. It's all good. Again, here's your. This is old school way of naming ketones here. This is butanone. They're calling it 2-butanone. Old school name is this is your ketone group, your carbonyl group, right? And they would say methyl ethyl ketone. That's how it was done for a long time. So just be aware. I don't think it's not a big focus. I've got so much to test you on. That's the problem with the final test, is you guys have put in so many hours of work and homework and quizzes and all this, and now what I got to test you on and make sure that you guys know everything from the whole course in an hour and 45-minute test makes it kind of difficult. So I'll be going for the strong things because I can't test you on everything. It's impossible. What do we got here now? Have a look at this one. Now, here, oh my gosh, this is a great one. See here, we've got a benzene group. And what do we got going on here? We got, there's a ketone going on. So, which is going to trump which? And going back to Alex there, it's not easy sometimes. In some case there, you go like an aldehyde, benzaldehyde. It has its own name. And when anything there that might give you trouble dealing with benzene, you guys have those sheets there, okay? And that is meant for some type of a guide there to assist you there with benzene. Because sometimes benzene's the big boss, sometimes it's not, okay? And like in this case here I have a benzene ring and here I have a ketone. Well, we can just looking at the name here, you can tell that the ketone is the big boss. All right, because its name is at the back. Okay, here we have ethanone. All right, and we have 1-phenyl ethanone. And you'll see there that when benzene is not the big boss, we use the name phenyl. Okay, and it's a good one. All right, look at this one here. Here I have a benzene, and here I have a propanone. Okay, 1-phenyl, 1-propanone. And you'll see there that it's attached there at the ketone. That's why we use a 1, because this benzene could be attached here. Okay? Or the carbonyl group could be here. And if the carbonyl group was here, it would be 1-phenyl, 2-propanone. That kind of a thing. Okay, so hopefully, Alex, there, that maybe that gave you a little bit more insight. And it's not easy. It really isn't. But you guys have all of your sheets there, and you'll have them ready to go. You guys got them for your quiz and your assignment. And if there's anything that's irritating you, just shoot me a question there, and we'll get through it, okay? What do we got here? Write the structure of butyl ethyl ketone. So this is an old school name. So don't freak out about it. You got a ketone. All right, so there's your ketone. And you got a butyl group, which is 4 carbons on one side. Nothing special. You've got an ethyl group on the other side. Okay, and they go alphabetical. Okay, and that's what this is. Butyl ethyl ketone. But what is its IUPAC name? 1, 2, 3, 4, 5, 6, 7. So it's a heptanone 3 heptanone. 1, 2, 3. And then 7 carbons. Heptanone. What do we got here? You guys can just have a look at these here. again, you find your longest carbon chain. So in this case here, it's an octane. And we've got our ketone group here. And if you're looking at this, okay, this will be your big boss here. This is going to trump everyone. So this is an octanone. All right, 1, 2, 3, 4. It's a 4-octanone. There's your base. That's done. Now work on your functional groups there, your side chains, and you've got a 2-methyl, 3, 4, 5, 6 bromo. Okay, and again, we've gone alphabetical. Okay. What have we got here? We got a 2,4-dichloropentanyl. 1, 2, 3, 4, 5. Pentane, pentanal. I don't need to put a 1 on the pentanal because we know that an aldehyde is on the side. And that's where we're going to start counting from. I know. The feedback I've got about the second half of the course as compared to the first half is a lot better. But there still are some little tricks of the trade there that you wouldn't pick up, if you were, thank you guys for being here in class for sure. Okay, because there's little things there that you pick up. And here we've got 2,4-dichloropentanyl. Any issues with that? Keep me posted, okay? We'll get you guys through it. Here is a perfect example. Okay? Now, this is not benzene. Okay? This is cyclohexane. Perfect example. Okay, so be careful. You will see this. All right? And this is cyclohexane. And we've got this ketone group on here, so it is cyclohexanone. And there's no need for a number because we could just turn this, and it'll always be on the number 1 carbon. So we don't need a number on here, okay? Is that okay? Any issues there with that one? Okay. Ketones, common use. Acetone, that's its old school name that we all know, but it's actually propanone. 3 carbons. Okay. Nail polish remover. Okay, that's it right there. Oh yeah, you really think you're getting butter in your cinema popcorn? No. Oh, and by the way, the whole idea of paying $20 for a bag of popcorn is ridiculous. They only use about 25 cents worth of corn, and they don't even really use real butter. Butanedione is the butter flavoring used in margarine. Butanedione. Butane, dione. Interesting, eh? Let's keep going. We've done this, oxidation of aldehydes. Okay, they will go. So here I have ethanol, primary, oxidizes there to ethanol, which can then be further oxidized into ethanoic acid. Carbon dioxides, their little suffix is oic acid. So methanoic acid, butanoic acid, that kind of a thing. And you'll remember there that secondary alcohols will only go into ketones and they will not go into carboxylic acids, okay? We're hitting this one pretty hard. Carboxylic acids and esters. Okay? You guys should be pretty good on esters there because of the lab. I didn't make the lab, but it's okay for getting esters in here. And it's kind of the same thing again, just changing with different molecules, but hopefully there you guys didn't have too much trouble with it. These are your carboxylic acids. Okay, they have a carbonyl group with an alcohol in the end of it. Now, these guys here, they happen on the end of a molecule. So you could just imagine there about the solubility. You remember, the longer the carbon chain that there is, the more difficult we can get this to dissolve into water. Well, here I've got not just 1 oxygen, I've got 2. So this whole side of the molecule is going to be very electronegative. Okay? You'll see it written here like this with a R group with a number of carbons. Acetic acid, which is vinegar. Okay. And here we have benzoic acid. All right. And what did we just look at up here? Was it one phenol? Where was it? And you'll see here, phenol with a ketone, one phenyl ethanone. The ketone is the big boss. And you'll see here that the carboxylic acid is also the big boss. It gets its name at the end. Benzoic acid. Okay. Naming, same thing. Okay, your carboxylic acid is always going to be on the end, so that will always be your number one carbon. So 1, 2, 3, 4, 5. This is a pentanoic acid. 3 carbon, I have a methyl, 3 methyl pentanoic acid. Okay. You might see these. I'm not too really big on these. You might, I think you might see somewhere here. When we're dealing with carboxylic acids, there's kind of a naming system that you might see. Okay, and your carbon here for your carboxylic acid is always a number 1, as we said. Next one is 2, 3, 4, 5, 6, 7. It just goes on. But what they will sometimes do is they'll use these letters here, alpha, beta, gamma, okay, to detail where, if there's something going on here on the number 4 carbon, what they'll do is instead of labeling this 4, they'll label it gamma. Okay, not a big deal. Again, one of those, you might see one question here or there. Not 2, just 1. Okay, and you just got to refer back to this slide here. And let's have a look at this one right here. Here, 1, 2, 3, 4. Okay, so this is a butanoic acid. All right, and you see, I like these ones because there's 2 competing groups on here. There's a carboxylic acid and an alcohol group. Now, which one is going to trump the other one? Well, your carboxylic acid will. So this is a butanoic acid and 2-hydroxy butanoic acid. You will sometimes see it referred to as alpha hydroxy. Okay, and just be aware. There might be one question. I'm making the test now. Probably not. Okay. Write a formula there for 3-chloro-4-methyl-hexanoic acid and alpha-aminobutyric acid. Okay. So, how do you draw these? You guys aren't going to be drawing them. You're going to be choosing which one, A, B, C, or D, represents the schematically what the English is saying. So how do I determine? Start from your backside. So, hexanoic acid. Okay, 1, 2, 3, 4, 5, 6. There's your hexane, and then there's your hexanoic acid. So that is done. Hexanoic acid is done. And now you've got 3-chloro-4-methyl. Okay, 1, 2, 3, 4. And remember, you're always starting to count there from your base, which is in this case here your carboxylic acid. Okay, alpha just means the number 2 carbon. So butyric acid, 1, 2, 3, 4. There's your butyric acid, okay, or butanoic acid. And your alpha is your number 2, and there's an amino, which we'll get into aminos there. We'll introduce them there today. We'll hit them hard there next week. But that PowerPoint is already up, okay, for next week there. I may modify it a little bit, but the information will not change. But please use that there for getting ahead, all right, because that covers their amines and these kinds of things. Hello.
In the previous slide, there's a question in chat, but what does uric represent?
Sorry?
So in slide 28, on the right-hand side, you've got the aminobutyric acid.
Yes.
What does the uric stamp represent?
It's an old school name. And you'll see here common name, and this is the same molecule right here. So the IUPAC name, 2-hydroxybutanoic acid. But sometimes when if you guys are ever working in a chemical shipment or getting chemicals there for the hospital or medicines, these kinds of things, you might see this called alpha hydroxy butyric acid. Okay, so the butyric acid is the old school name for butanoic acid.
So they're still transitioning from the common names to the IUPAC names?
There will never, there's always going to be those who like, generally everybody knows the IUPAC name, okay, because that's kind of the international, okay,
Right.
but there are old school names out there like isopropyl alcohol. We all know that one, okay, but its IUPAC name, okay, is 2-propanol.
Okay.
So where my focus is, 99% of my focus there for this course is IUPAC. But you might see an old school name 1 or something like that out of a 60-mark test. So I'm just showing this there that you guys will be able to refer back to this slide if need be in a testing situation. Is that okay?
Perfect, thank you.
It's all good. Good questions. I like them. Great. Ask away. Did we hit this one already? Am I losing my mind? Could be. Yes, I did. So don't be afraid of these old school names. They're not a focus of mine. The IUPAC, if you didn't study anything to do with old school names, you'd still be able to get 96%. So I think you guys are doing all right. Here are just, again, maybe 1-mark question here. Methanoic acid is actually the old school name. It's called formic acid, which in a biological, we were just watching, actually there's a really, really good TV show there on Netflix called 72 Dangerous Animals. And they've got a whole series there, South America, Southeast Asia, and the whole thing. And great for the kids. It's not really scary, so it's good for my kids anyway. But red army ants there, they'll sting you, and it's called formic acid. That's what they refer to it as, but the chemical name for it, the new IUPAC, is methanoic. Okay, you've got ethanoic acid, acetic acid. That's its old school name. Common name, vinegar. And you'll see these all right here, okay? And yeah, very good. Solubility, okay, of carboxylic acids. Again, we're in and around the 4 and 5 carbon. That's the cutoff for solubility. And you'll see here 1 to 4 carbons. So if you have a 1, 2, or 3, or 4 carbon chain with carboxylic acid on the end, it'll go into water. Generally, anything above 4 carbons, it's not as good, and then eventually it just won't. So 4 to 5 carbons is your range in there somewhere as far as solubility goes. Okay. Just for one of those questions there, if I give you methanoic acid, ethanoic acid, propanoic acid, and butanoic acid, which one will go into water the best, second, third, and fourth, and you'll know there that it's based on the carbon chains itself, okay? Like, the nice thing about this test is you guys know what's coming. There's no tricks. There's no tricks. If you're, I know you guys are hitting the quizzes and you guys are hitting the assignments. The test is going to mimic that 100%. I'm just going to use different questions, and instead of using pentanoic acid on the assignment, I'm going to use hexanoic acid for the test. So I think you guys are in good sorts here. Boiling points. Generally, carboxylic acids there, they have a higher than normal boiling point because they have 2 oxygens there, which are capable of producing double the hydrogen bonds. Okay, And if you got double the hydrogen bonds there, that means that it's a more solid liquid. Hopefully it's a more cohesive liquid. All right. And you're going to have to take a lot of energy to get this thing to boil. Okay. If you look at nonpolar substances like ethane, methane, even have you guys ever noticed there when you're sitting, they really don't have them anymore, full service gas stations, you sit in your car, buddy comes up, he says, do you want to fill it up? Yep, fill it up regular please, thank you. And you're looking in your rear view mirror, you're sitting there playing with the music or whatever while he's filling up the car, and you can see through the rear view mirror there at the side of the car, you can see these vapors emanating from the gas tank. Well, this gasoline is 100% nonpolar, and if you look at what's on the screen there, carboxylic acids, water, polar substances that can hydrogen bond. This, like the whole, that's why water, you flip you dive off a diving board and land on your back, you could potentially do some serious damage to yourself, because water is very strong because of this hydrogen bonding, where one atom is in essence, one molecule is in essence attached to another molecule, if only for a fraction of a second. But you've got this going on a billion times a second within a glass of water. Okay, it's very cohesive. They're all together. But going back into getting your gas tank filled up, you see these vapors emanating because non-polar molecules like gasoline, they don't have any attraction to each other even. There's no cohesiveness. And that explains gasoline is very volatile. It's easy to evaporate because there's no attachment to another molecule. That's kind of the difference between a polar liquid and a non-polar liquid. All right? There's no attachment at all from one molecule to another in a non-polar liquid. All right? So that's why they're easy, they're very volatile, they're easy to evaporate. They want to get away from each other, but not so when it comes to a polar substance. What do we got here now? Ionization in water to produce a hydronium ion and ions. Carboxylic acids tend to be weak acids. Okay, like you think back there to last, I want to say last semester, but it was this semester. It seems like so long ago. The first half of this course here. You remember your definition of a strong acid and a weak acid. Strong acid, 100% breakage, 100% ionization, hydrochloric acid, these kinds of things. All right? Dangerous acids because they break 100%. Weak acids, 50-50. Okay? They don't break 100%, so that's what makes them weak. Carboxylic acids are weak acids. Okay? Like vinegar, lemon juice, these kinds of things. They're not going to whack you. All right? Phenols, benzene with an alcohol, okay, are in general even weaker. Okay? And you have to think here, you've got this benzene, polar or non-polar? Crazy non-polar. Okay? So you've got this heavy benzene ring sitting on this polar side group here, and you got to think there that a phenol is even a weaker acid, all right, than carboxylic acid. Carboxylic acids are released into the blood by the liver in an excessive amount during ketoacidosis, which is a condition associated there with uncontrolled diabetes. Okay? Start to get fruity smells coming from the mouth. Normal amounts of carboxylic acid can be controlled by blood buffers. Okay? Carbon dioxide coming from my big toe en route to my lungs to be expelled by my lungs. The body is ingenious, takes carbon dioxide, changes it into bicarbonate ion, which is kind of a weak base. All right, and it can soak up some of these little acids there in the blood. Okay, so here we've got this one, levodopa. Okay, is a carboxylic acid used in the treatment of Parkinson's disease. Okay, and good little thing here, you can test yourself. There's a benzene, and I wouldn't ask you anything like this to name this IUPAC, because I got 2 alcohols in here. I got a benzene, I got an amino, and I got a carboxylic acid group. I got fourth, and you've got an aliphatic chain here. I wouldn't give you something like this, okay? I would never ask you guys to name something like this. It's beyond where the scope of this course is meant to go, okay? But do know Parkinson's, carboxylic acid, and we got a name here. And by the way, we'll get into L and D. We've kind of already touched them a little bit. We'll go back, okay? Major types of carboxylic acids. Here you've got an unsaturated carboxylic acid. Okay, sorry, I'll zoom in. It's called oleic acid. And unsaturated, you'll see that there is a double bond in here. Okay, it's a rather long molecule, and here's your carboxylic acid there. Okay, aromatic. Here we've got benzoic acid. You can even have dicarboxylic acids like oxalic acid. Okay, that's a nice one. Dicarboxylic, oxalic. And I wouldn't ask you IUPAC names for these. Like, for some chemicals, we only use IUPAC. For other chemicals, we only use old school name. That's how she goes. Depending upon what further organization you work for, they will choose one way or the other, and that's what it'll be. Okay. Hydroxy acids. Okay, so there's your carboxylic acid here, but then you've got an alcohol group on there. Okay, lactic acid, amino acids. That's what we're gonna look at in the next little bit. These guys are great. They all look the same. These are the building blocks of protein, muscle. Okay, and basically they're a 3-atom chain: carbon, carbon, nitrogen. And on one side, you've got a carboxylic acid. On the other side, you've got an amino group, which acts like a base. You've got a carbon with a hydrogen. So amino acids, they're all the same except for this R group. And it's this R group that creates this 3-dimensional structure that we know about proteins. Like if you go and Google hemoglobin, it's massive. Well, it's not massive, but if you blow it up big enough, it looks massive, right? And when your body's making proteins, they're in the ribosomes. Okay? You know, your mRNA comes out, goes there to the ribosomes there, and with the tRNA starts building proteins, 1 amino acid at a time, right? You guys have all seen that slide there in Bio 1031. You know, you get 1 amino acid is brought in, and then another one, and then another one, and then another one. So you've got this chain of amino acids, right? It's kind of like a primary chain, just a chain, all right? But you have to think your body is polar. You're just a great big bag of salt and water. Salt water, that's all we are. So we're polar, all right? So the cells, the fluid in the cells is polar. Everything's polar. And what the body will do now is, as it's making this protein, it'll start putting non-polar R groups on there. So you'll have sections of amino acids that have polar R groups. These guys here will be exposed to the body inside the cell. But then, because proteins, you know, enzymes, they have this 3-dimensional lock and key, right? Amylase in your mouth. It only locks onto starch. Breaks it, all right, and then moves on. Well, we need this 3-dimensional shape in order for this enzyme to work. So how do we get this protein to fold up into this particular space that is going to work to break down starch? Well, it's all the different R groups. And what the body will do is when it's making this hemoglobin or whatever protein you want, and we need this certain configuration, well, we're going to start putting non-polar R groups in there. So you start getting your amino acids that start to have non-polar R groups in there. What will happen now is they will start to fold and get away. So the non-polar R groups are now kind of inside the molecule. So that, and it twists and turns, and it conforms into this 3D shape there that is now usable to go out into the body and do work. So it's we'll talk more about amino acids there in a little bit. Like right now. Okay, I've already said there they've got a carboxyl group or a carboxylic acid group. They've got an amino group. Okay, one acts like an acid, the other acts like a base. And what will happen is when you put an acid into water, okay, the hydrogen pops off, okay, and goes on to the water molecule, which changes into hydronium, right, H3O+, all right? And so this hydrogen will pop off. And what will happen is the hydrogen will go right onto here and make NH3, ammonium, all right? And it's called autoionization, okay? So amino acids, they are the building blocks of protein, and there's about 20 of them there, okay? And they all have these different R groups that will affect its three-dimensional shape once this protein is made, right? Because there's hundreds of these amino acids in a protein, possibly more. Write the structural formula of the following. Here we have a dicarboxylic acid with 3 carbons, okay? So here's the dicarboxylic acid. 3 carbons. 1, 2, 3. Okay. What do we got there? Good. We got an amino acid, okay, with 3 carbons. Okay. I wouldn't ask you to name this. You guys can find the name out on your own, but the whole point of this is knowing where a dicarboxylic acid is. I wouldn't ask you to name this. I'm not even going to give you a name. Don't ask. Okay, because I don't want to confuse you. You guys we built an information library, and I don't want to destroy it by throwing something there that I will never ask you. Okay, so an alpha amino acid there. Okay, alpha. What does alpha mean? You have your 1 carbon. Alpha will be your 2nd. Beta will be your 3rd. Gamma will be your 4th. That's as far as I'll take it, okay, if I do take it at all. So here we have an alpha amino acid there with 3 carbons. There you go. That's what that one is. Back into the oxidation. There's your alcohol to an aldehyde to a carboxylic acid. Okay, we've been all over that like a duck on a June bug, as my grandmother would say.
Sorry, Ian.
Yeah, what you got?
I have a question about the amino acids.
Yeah.
Are they always going to be found on like the end of the chain, or could they be found in the middle of the chain?
Okay, what do you mean an amino acid is like you got your muscle, you got your bicep, all right? It's all muscle. And if you break it down into smaller pieces, the smallest piece of protein or muscle is going to be a single amino acid unit. Now, clarify for me what you meant by chain on the end of a chain. Which chain are we talking about?
Sorry, I meant like
No,
the
it's
two
all good.
functional groups.
Sorry?
So like the two functional groups, like you know how like when alcohol, with alcohol it's on the end and it'll be called an aldehyde.
Yeah, okay.
But it can also be found in the middle and it'll be something different. Like I was wondering if it's like always found on the end.
For these guys here, like how I want you guys, actually it's a great question. How I want you guys to think about amino acid. Think about it as started off with a carbon in the middle. And it's basically just a cross. So your carbon is in the middle, right in here. All right? And you're going to have a carboxylic acid off to one side. You're going to have an amino group off to another. You're going to have a hydrogen off to one. And then your fourth bond, because carbon's got 4, will be an R group. That's how these guys work. Tell me if I answered it and if I didn't, explain it to me another way.
No, I got it.
It's okay?
Thank you.
So these amino acids, there are the small little molecules that have a carboxylic acid and an amino group on either side. One's an acid, one's a base, and it's quite ingenious. The body, I'm still learning about the body myself, and it's just ingenious how over evolution the body utilizes these little molecules and creates muscle and movement and everything from these. So that's what we're going on here. Holy, it's getting warm. Actually, no, that truck is gone. I could open up the window. Where are we here? Yep, we just did that one there. What primary alcohol can be oxidized to form pentanoic acid? I love this question because, first of all, you got to know what pentanoic acid is. You got to know the structure of it. So you got to basically go to the answer and work your way back to find the question. That's what we're looking at here. So what primary alcohol can be oxidized to form pentanoic acid? Well, you got to backtrack now all the way back. And pentanoic acid, carboxylic acids are always on the end. So that means there that 1-pentanol is the answer. Okay, so you got to work backwards. So first, this is pentanoic acid right here. Work backwards there. What would be the precursor to this one? What would 1-pentanol change into initially before going to pentanoic acid? It would be pentanal, an aldehyde, right? That's the precursor there that the question is missing. But that's how this would go. 1-pentanol to pentanal to pentanoic acid. Hopefully that's all right. Talk to me if it's not.
Can you go back through that?
Yeah. What were you? What's giving you trouble?
These questions in general give me trouble because I don't understand. I don't know how to work backwards. Makes sense.
Well, right here we've covered this. I'm just gonna go through here. Oh, right here. Very, very good slide to know. Okay, we've hit this pretty much every week, I think. I don't know if we covered this in week 8, but definitely week 9. Just this oxidation, starting with an alkane, and then first oxidizing, we can change that into an alcohol. A second oxidizing is if this alcohol is primary on the end, it'll be an aldehyde. And then another oxidation of the same molecule will change into a carboxylic acid. So basically, when we're trying to do that question like we were just trying to do, I gave you this, and I'm asking for this one here. So as far as working back, and Alex, you don't have to think of it as working backwards because there's double arrows. So it all depends on which way you're looking at it. You're going forward. If you're going this way, you're also going forward here. How are we doing here?
The whole thing is just kind of confusing when it comes to those, but I'll just have to go through.
Well, it's right here. And just the whole idea of an alkane, oxidizing it. You're oxidizing, adding oxygen. So first step in adding an oxygen, right here. Second and third. Now, just remember, if this is a primary, that means the alcohol is on the, basically the end carbon. This will go all the way to here. But you remember, if your alcohol is on an inside carbon, a secondary carbon, it'll go to a ketone this slide isn't explaining it properly. The other slides there that we've covered this there before are, but have a look at those ones there. The big difference there between a primary alcohol and a secondary and a tertiary. Okay, and being able to work backwards, there's your slide right there. Okay, but there's a lot more slides there covered last week and the week before on that as well. Okay, and if you guys have issues with that, just shoot me an email. It's all good. Now, I have no idea where I was. No, that doesn't look familiar. Yes, right here. So, this is the question there we were looking at. What primary alcohol, okay, so that gives you some information there, can be oxidized to form pentanoic acid? Well, you'd have to draw your pentanoic acid or have an idea of it, and then according to one of those slides there that I just showed you, work your way back. Okay. Moving on to what is an ester. Now, you'll see here, and you guys should be all on top of esters there for sure. Here you have a carboxylic acid and an alcohol. That's how these guys go. And through dehydration synthesis, we suck out of water. Okay. And we get this. A C double bond to an O, and the C is also bonded to another O. There is your ester bond. All right? And these guys here are really smelly. Okay? Because this isn't really, it's not as, there's a lot going on here. Oxygens, there's a lot of electrons, very electronegative. So within this small amount of space, there's a lot going on, and that's why these guys here tend to be quite smelly. In a good way and a bad way. So naming these guys. So name the alkoxy group. This is the alcohol portion of the molecule. So you see what we do is we break this up into two pieces. The first piece, C double bond O. That's where you cut it. All right, and then you have the O attached to the other group. All right, so you name the carboxylic acid, okay, with an 8. The alcohol, I'm just going through this. We'll explain there with more, and it'll make more sense. And the alcohol portion, okay, is named first, followed by the name of the acid portion. So here we have, look at this one right here. Here I have an ester. But I have an F and a meth. Okay? So here I have ethanoate. Because why is this one here an O8? Because this carbon has the double bond. And this one here does not have the double bond. Okay, so it's just a methyl. And how we do this, methyl ethanoate. The O8 goes on the end. Okay, so whichever carbon, whichever side of an ester has the C double bond O, that one there will be at the end. But I think you guys are okay with this with the lab. Yeah. This is what we got here. Here we have propanoic acid. And here we have methanol. And you've got your old school names here. Okay, not interested in. Okay, so I got propanoic acid, methanol, and here we have methyl propanoate. Why is it propanoate? Because the propyl group has the double bond O. That one there will go at the end. All right. What do we got here now? Naming these. I gave you the names here. They're all here. But try these out. You got 1, 2, 3. So I got a propyl group here. Whoa. Here I've got an ester. All right. And I got a 1, 2, 3, 4. Okay. So which one's attached to the double bond? Okay. 1, 2, 3, 4. So this one here is going to go at the end. So that'll be a butanoate. So here I've got propyl butanoate. Have a look at this one. Oh, the dreaded benzene rears its ugly head again, eh? And you see here you've got two competing groups. You've got a benzene and you've got an ester. In this case here, generally the functional group will trump the benzene. And because the ester isn't attached per se, but we'll see. And you have a look here. You've got phenyl ethanoate. And you see there the phenyl group. All right, it doesn't have the double bond. All right, the eth group does have the double bond. Okay, so there's your ethanoate, phenyl ethanoate. I know it's not easy sometimes. Some of these can just confuse you like nuts. You guys can have a read of this. There's that word volatile. Low molecular mass esters there. So smaller esters, volatile, means that they don't need a lot to evaporate. Okay. Paints, varnishes, lacquers, these kinds of things. Fruity odors and fragrances. That's what these guys are here. All right. Love it. There's the sounds of summer. High molar mass esters there, non-polar solids at room temperature. They tend to be waxes, all right? Kind of heavier, and they're solid at room temperature there. You guys can have a read of these, and they're just there if there is a question on the go. Getting back into amino acids there, an alpha amino acid. Again, they've got the carboxylic acid and the ammonia group there. There's your general formula for an alpha amino acid, okay? Alpha amino acid. Alpha is your second carbon. The amino group is off the second carbon. The R groups I've kind of already talked to you about. These are the ones there that can, depending on what they are, they can cause the growing amino acid chain, okay, which is a primary structure. It can now turn and make beta sheets, alpha helix, okay? What kind of species would be on the inside of an alpha helix? Generally nonpolar, right? So there's all these different things there. You guys can have a look at these when we're talking about protein structure, okay? And all these different R groups there. You've got nonpolar, you've got polar, okay? You can have amino acids there that are extra acid. You can have amino acids there that are extra base. All they do is they add an extra carboxylic group or a nitrogen group on there, okay? They can be polar and nonpolar. And this is the versatility that the body, I guess all living organisms have developed this process of utilizing this tiny little molecule that we call an amino acid that is so versatile. You can start chalking amino acids onto each other, growing longer chains, three-dimensional structures, proteins. It's incredible. Again, more of the same here. Okay, just talking about basic, neutral, and acidic there combinations. I'm not too worried about ratios there. I'm more worried about naming and chemical chemical reactions, that kind of a thing. You can have D and L, and we're going to talk more about these guys when we're going to talk a little bit about sugars there next week, okay? And you'll remember there when you have optical isomers, you'll remember there the stereoisomer. Write this one down, stereoisomers. That was, I think it was week 8, it might have been week 9. Okay, when you have a carbon with 4 different bananas on it, remember that one? Okay, you can have, and you'll see here, have a look at this one. Here are your alpha carbon, your center carbon, and let's start from the top and work clockwise. So here I have a carboxylic acid, here I have a carboxylic acid, same. Here I have a hydrogen, oh, here I have an amino group. Let's continue, oh, there's a methyl, and you'll see there that these two are exactly the same chemically. They have the exact same reaction. There is no difference in boiling points or melting points, but what they do have is they are different in that they rotate light because they are not the same. They're called stereoisomers of each other, okay? And the atoms are in a different orientation. Significantly? No. Enough to change light? Yes. Okay? And that's your D and L. When your amino to the right of the alpha carbon, okay, an L is when your amino is to the left. Okay? We'll get more into that there next week. I'm just kind of foreshadowing. That's all we're doing there. Okay? The amino acid has one chiral carbon atom, which is shown in red. So have a look at this amino acid. It looks crazier than these ones, okay? But it's really not. And you'll see here that there is your alpha carbon. There's your carboxylic acid. There's your hydrogen. And there's your amino group, which every amino acid will have. It will have those three. The only thing that's different between amino acids is the R group. And you have a look at what we have here. We got a massive benzene. And that is benzene. So this is hugely nonpolar. So that's going to, by itself, it's really not going to change this molecule at all. But if you put 10 of them in a row in a polypeptide chain, now you've got this hugely hydrophobic, scared of water section that will probably turn into itself, and now you've got some three-dimensional structure going on. Okay? But good little question there. Where is the chiral carbon? Where's the carbon there that has 4 different bananas coming off of it? And there's only one of them, and it's dead center. Amphoteric just means that it can be an acid or a base, like water, right? Water can act like an acid, or it can also act like a base. Remember Lewis acids and all these kinds of things. Amino acids can do the same. That's why they're so important. Okay? And you can have a look at the what goes on here. If you're talking about a basic reaction, okay, that's going to involve there your amino group. If you're going to talk an acidic reaction there, okay, now you're talking there as far as the acid group goes. So just if you put an acid with an amino acid, the acid is going to go after the base part. And you see right here, an acid, if you add an acid to this, there's your hydrochloric acid and your amino acid, that hydrogen is going to go right onto here. Okay? So in this case here, an acid will work like a base. Hi. Sorry. Yeah. Get that dog out of here. Get some exercise there, Harley. And this one here, if you have an amino acid with a base, well, this base here is going to attack the acid portion of this one right here, and you'll see what goes on there. Okay? This is a good one. Zwitterion, self-ionizing, autoionization. It's like I said there before, amino acids can self-ionize. So this hydrogen here can sometimes just pop right onto the base side, and this is alanine, okay, the amino acid, but you can also have an alanine Zwitterion, okay, and you see there that the hydrogen has just jumped right on there. Doesn't affect the chemistry. It's just ready to go there. It's in solution. And again, all these amino acids can act like an acid or a base. And the same kind of thing right here. You guys can have a look at this and how it reacts in a basic solution, how it reacts in an acidic solution. Okay? Leading there into next week, because next week there is the last lecture, okay, which is already posted. I'm going to have a look at it there this weekend and get it all cleaned up there. But the information is not going to change. I'm just going to probably make it easier there to, I update my PowerPoints all the time. So you guys are going to see there that when two amino acids come together, okay, it's called a peptide bond. I'm sure you guys have heard of that already, okay? And a peptide bond is, I'll show you right here. So here you have your amino acid. Okay, there's your carboxylic and there's your amino end. Okay, so your carboxylic acid end of one amino acid, and this is going on in the ribosomes. This is how they make protein chains. The carboxylic acid of one meets up with the amino end of another amino acid, and through dehydration synthesis, sucks out of water, and in that process right there, we get this bond right here. And I'll just slow it down. You see this right here? So C double bond O to an N. This is called an amide bond. A-M-I-D-E. Amide bond, which is just another word for a peptide bond, which is just another word for a peptide linkage. Okay? So, and we're going to get into more of these there next week, but I just wanted to introduce these to you. Okay? Next week is going to be all about amines. Amino NH2, and it'll also be about amides. Okay? And the last slide here, the amide bond is your peptide bond, neutral nitrogen-containing compound, not acidic, not basic, molecules both in aqueous and as a pure substance. And what's interesting here is it contains this carbonyl group directly linked to this amino group. Okay? And that's called your amide bond. But other than that, that's what I got. I don't want to keep you guys any longer than you need to. I'll post this there to YouTube. I hope you guys are doing well. Stick around if you guys have any questions other than that. Yesterday there, I had some stuff there that I needed to do. I apologize for that. But if you guys have any questions there about Lab 6, stick around. We can talk about that there. We'll get you guys sorted. But other than that, y'all have a great day. Take it easy. Go get some sun. That's all I got. You guys have any questions there? Talk to me.
I have a question.
Who am I speaking to?
Shaylin.
All right, and yeah, I don't know. Yeah, talk to me here. Questions. We'll keep it recording. What do you got?
Okay, so there's like a few of them that I want to ask you about. The first one is number 39 on assignment 3.